friction, because that's what we were talking about as the heat transfer mechanism that we're the most familiar with. And just in general, internal energy, we'll talk a lot more about the concept of internal energy and Q, which stands for heat, next semester in the beginning of the class. But generally, macro scale is what we've been dealing with. That's everyday objects. It's like things that you can see and touch as a human, okay? That means like a ball, a table, you, okay? That's the macro scale. So that means we have, those things have a mass, they have a velocity, just as a whole object, okay? When we talk about micro scale, that means sort of all of the same physics applies to some extent, but in like the microscopic world. So when we talk about friction, right? Friction, we're just calling this constant, especially for kinetic friction, we're just calling that a constant force value. But what's really happening if you get down with like a tiny microscope is that you have all these little tiny molecules that start bonding and breaking bonds, and that's what's generating the heat. There's like, on the microscopic level, it's like a war zone every time you're seeing friction, okay? So there's a lot of masses and forces and electromagnetic interactions. We're just calling them one bulk thing. So microscale is if you want to get real nitpicky about what's happening to every individual molecule. Macroscale is like, well, we know all these molecules kind of act the same way and we can get this bulk effect, okay? So when we talk about this in terms of energy, the total mechanical energy is the kinetic, 1/2 mv squared, and then there's also rotational kinetic, which we haven't talked about yet, and then the potential energy, which is like springs and gravity, right? And to some extent, there's also electromagnetic potentials. We won't talk about those till next semester, but same idea, okay? All we care about now, springs and gravity. The same sort of things happen on the microscopic scale. So like, for instance, if you think about chemistry, when we talk about atomic bonding, we can sort of model those as springs. There's still like gravitational attraction between molecules and atoms. It's small, but it's not insignificant. So all of these, molecules moving, right, that, well, let's see. When you have a gas, what are the molecules doing? Versus a solid, right? Solid, they're kind of hanging out. Maybe they're vibrating. They're like, if they're a gas, they're like all over the place, okay? So that's what we mean by the microscopic kinetic energy. The microscopic potential energy could be like the atomic bonds. And all of that, since we can't just like, whenever you do a problem, you're not talking about each individual molecule. That would be insane. So we just call that all like internal energy, and it encompasses all of the kinetic and potential energy on the microscopic level, okay? Okay. So when we talk about dissipative forces, remember, what kind of work does friction do?
Negative.
Always negative, right? Because the frictional force always points in the opposite direction of the displacement, okay? So if you consider dragging this box across the floor at a constant speed, the net work done on the box is going to be the change in distance, right, times the frictional force. And why can't we just multiply them instead of integrating them? Why don't we have to integrate friction? When do we have to integrate to get work? What kind of forces? I can wait. It's a great question. Why do we have to use an integral for work? What situations does that happen in? Non-constant forces. And what do we know about kinetic friction? Well, that is a constant force, right? It's just mu n. It has nothing to do with the displacement, so we just multiply those together. So the work done by friction is negative, and it's going to be this times this, okay? And then there's also work done by this tension, which is going to be this times this. So the net work is this minus this times this, okay? However, if we want to figure out the change in internal energy, that's going to probably be the net work done by friction, because we know the frictional work is slowing this thing down, and so that energy has to go somewhere, and it turns out pretty much all of it goes to heat, some of it goes to sound. Okay, so that means our change in internal energy, in this case, right, all those molecules rubbing together creating friction, is just the work done by friction. Okay, so that's just friction times the displacement. So the increase in internal energy is equal to this product, and it depends on the path length through which the block moves. Okay, because remember, we have path-independent forces. Those forces we call conservative forces. So when we talk about gravity, right, it doesn't matter if I get the ball to here or if I move it up to the same height this way. It only matters this distance from this height to this height is all that matters. However, if I'm dealing with friction, it matters if I drag the ball this way or if I make a snake pattern. Right? Because then the total displacement actually matters because this is a path-dependent force, okay? It's a dissipative force, which means more dragging means more heat, okay? So just to remember, if we're talking about change in height and gravity, the path doesn't matter, but if we're talking about friction, the path does matter, okay? Okay, so if we want to break this same thing down, right? This is that same equation, because remember it's change in kinetic energy, change in potential energy, change in internal energy on one side, and then all of the possible transferred energy on the other side. So we're just setting a bunch of things equal to zero because we're not dealing with a lot of those other variables, and we're saying, okay, work is going to be equal to the change in kinetic energy plus the change in internal energy. All right, but there's also lots of ways you can express this. You can either include, remember, this is only if the friction heat stays in the system. If it's leaving the system, then this goes on the other side as work, okay? So that is tricky. So we'll do an example to demonstrate this. Okay, so let's say we have a 6 kilogram block. It's initially at rest, and we pull it to the right along a horizontal surface with a constant horizontal force, probably tension, of 12 newtons. And we're probably saying tension because we're pulling, but it doesn't really matter. We want to find the speed of the block after it has moved 3 meters if the surfaces in contact have a coefficient of kinetic friction of 0.15, okay? So the first thing we're going to want to do here is draw a picture, and let me draw a picture. So we'll start with this guy. So here's the ground. And we'll say the coefficient of kinetic friction is 0.15, so we're going to put that there. We have a 6 kilogram block. Initially at rest, and we know it moves over here. So let's see, mass 6 kilograms. We want to draw our forces. So what forces are acting on this block? Gravity.
Normal force.
Normal force. Anything else?
Friction.
Friction. What kind of friction is that?
Kinetic.
Kinetic friction. So that's going to be mu k n. And then we also know that we have this force, the pulling force, so that's going to be, I'm going to call that tension, okay? What's the initial speed? And then we want to find the final speed, which let's just call v. So that's what we're looking for. And then one more thing we want to include is the distance. So that's just going to look like this. So delta x is equal to 3 meters. Okay? So we want to set up our equation. The equation we're just given is, and I'm going to make this a little bit smaller so it doesn't take up so much space. All right. So the equation we were just given is that if we set up all of the sum of all the work, that should be equal to the change in kinetic energy plus the change in internal energy. Okay? Now there's a couple different ways to do this. Let's start with picking the boundaries for our system. So what are the boundaries for our system? What do we want to call the boundaries?
Block in the surface.
You want to do the block and the surface? Okay. So what are the other options? Yeah, so we can pick our boundary to be just the block, or we can pick our boundary to be the block and the surface, okay? If we pick our boundary to be the block and the surface, that means the frictional energy lost is going to be inside of our system, okay? So when we set this up, what's the work here? Is there external work? The pulling force should be external work, okay? So we're picking our system. Let's start out with this. System is, actually we can put this up here. So system is block plus ground, okay? So that means there's an external work of the tension. And how do we get the work? Tension times what? Work is force times what? Distance. So tension times delta x. That's the external work, okay? What about the change in kinetic energy? What's our final kinetic energy?
0.
The initial 0, right?
We don't know final.
We're looking for the final. So 1/2 mv squared minus 0, which is the initial kinetic energy, because remember this is change in kinetic energy. And then our change in internal energy, well that's going to be our frictional force times delta x, okay? So that's work, but it's inside the system. So it's the internal work, okay? So what are we solving for here?
V final.
Yeah, V final. So we're gonna just do some algebra. So this is T delta X 1/2 mv squared plus friction delta X. The friction, we're gonna have to go over here. Remember, we know that N is equal to mg. We're just using Newton's second law over here. So this is really the sum of the forces in the y direction is normal force minus mg equals 0, but we're shortcutting a little bit. And then we know that tension should be, let's see, along the right. It does not have a constant speed. So tension we're just going to ignore, but we know that friction is equal to mu k n, so that's going to be the same as mu k mg. Okay, and it's important to do this. It seems like friction will almost always be mu mg, but what about if you're on a slant? Is it mu mg then? No, then you'll have a cosine or a sine of theta. So it's important to sort of draw out the force diagram, make sure that you know what your friction is going to be. So this becomes, tension delta x is equal to 1/2 mv squared, and that becomes mu k mg delta x. So we solve this for v. So v is going to be t minus mu k mg delta x times 2 divided by mass, and then we take a square root. Okay, so we can sum this up by plugging in our numbers. That's going to give us 2 times 12 newtons minus 0.15 times m, which is 6 kilograms, and g, which is 9.8 meters per second squared. We're running out of space here. Hang on, I'm gonna make this smaller so we have space. All right, and then that's multiplied by delta x, which is 3 meters, and divided by the mass, which is 6 kilograms, okay? We plug all that stuff in, and it should give us 1.8 meters per second, and that's our speed. Okay. that's what happens if we get a system that's block plus ground, all right? How would this look different if we pick the system to be just the block? So if we go back to this part of the equation, let's say we picked a system that is block. Okay, now which forces are considered outside work? Friction and tension, okay? So on this side of the equation, instead of tension, right, it would look like tension minus friction, delta x is equal to 1/2 mv squared minus 0, okay? If you look at the way this is written versus this one, all you have to do is rearrange the pieces, the negative sign. So this has a positive sign here. Because there's a negative sign here, it gives you the same equation, okay? But it's important to keep track of which things are inside and outside of your system because it tells you which side of the equation to put them on, and it should give you the same answer if you set everything up correctly. All right? Any questions on this one? Cool.
Okay, so here we have a block of mass 1 kilogram. It's attached to a spring. So instead of like the earlier problem where we're just pulling something with a tension, we have a spring. We know what this spring constant is. We know this spring starts out compressed and then is released from rest. And then we want to calculate the speed of the block as it passes through the equilibrium position. And we say there's a constant frictional force, and it's given to us, so we don't need to calculate it this time. And that's constant from the moment it's released. So the first thing we want to do is draw this out. Oops. So here we have our, it's slightly, we have a block At first it's compressed. Okay. So I'm going to do this as the before, and then this will be like an after. All right, so after this block moves over quite a bit. I'm drawing this not quite to scale, but you get the idea. So this is back to the equilibrium position of the spring. It's not drawn very well. So we know this is our initial situation, and this is final. Okay, so let's color in our block. And then we also know this is the floor, which has friction. We have to keep track of all of the variables that we need. So there's also we know the displacement. So this was going to be x equals 0. This is x equals 2 centimeters, which means that our displacement delta x is 0.02 meters. We know our speeds for each thing, so our initial speed equals 0. We want to figure out what our final speed is. That over. Because that's the thing we want to calculate. So calculate the speed of the block at x equals 0. Remember, we're going 2 centimeters. So that would be -2 back there. We also know there's friction. So, if we want to choose what our system is, it's also normal force and weight, but we can ignore those for now. We want to choose our system. Let's start with this equation we use. So, start with the equation. Remembering this is just part of the total picture because you could include delta U and you can include all the stuff over here, but we're just not seeing that here. In this equation, we see there's a spring, we see there's the ground. So we want our system to include block and ground. Okay, which means that the spring is considered an external force. So the work is the work from the spring. The change in kinetic energy is final minus initial. So 1/2 mv final squared minus 0. And our internal energy is just friction times delta x. What's tricky about the spring is because work done by a spring force is variable, we have to write this as kx dx from 0 to 2 meters, which ends up being 1/2 kx squared, but let's just get there. So this becomes 1/2 k delta x squared. If you do the integral, 1/2 mv final squared plus friction delta x. We solve this for our velocity because that's what we're trying to find, and that gives us 2/m 1/2 k delta x squared minus friction delta x. Plug all our values in. That's 2/1.6 kilograms, 1/2 thousand newtons per meter, 0.02 meters squared, minus 4 newtons times 0.02 meters. Let me make that look better. And then when you plug all that in, it gives you 0.39 meters per second, which is our final velocity. So again, we're just looking at our initial and final values. There's another way to solve this, which is if you want to consider the spring to be potential energy. So let me just show you that really quick, and we'll make this small so we can get it out of the way. So if we chose a different system that included the spring, then we use, whoops, that actually is an isolated system, but we have to include potential energy now. And since we know this is 0, this becomes 0. 1/2 mv final squared minus 0 plus 0 minus 1/2 k x squared minus friction delta x. And you can see this is pretty much the same thing because this term ends up being negative, so it's the same as bringing it over here. So no matter how we set this up, as long as we know the boundaries of our system, we should get the correct answer because this equation will end up looking like this equation.
A clicker question. Oh, okay, so it's a pretty broad spread of answers. Please discuss, we'll vote again. Lost a couple. All right. We're mostly thinking T, but C is a close second. So, obviously it doesn't all go to the road and it doesn't all go to the tires. Some of it's going to be heat in the road and the tires, and then some of it's going to be what else? Sound, right? So C is the best answer. It's not all transferred away from the car because some of it stays in the tires, which is why it's often a good thing, like we did in the first part of the last problem, to include internal energy, to include in your system things like the road, because not all of the energy leaves the car. It all turns into thermal energy, right? So some of that energy ends up in the tires, which will get dissipated, but like it's a little bit more complicated than all the energy is just gone. Okay, so it doesn't all leave the car. Some of it stays in the tires, some of it goes to the road, some of it's sound. Okay, and this is why we like isolated systems, why we started with isolated systems, because they're much less complicated. You're not losing anything. And so it's often really hard to account for energy loss due to things like friction and collisions because there's so many different ways that things can go. Okay. Okay, so that's the answer there is going to be C. And